behind me is a cubic polynomial, and suppose it has real roots r1, r2, and r3. And suppose that all of them are either positive or negative. Now, what's so cool about this is that if you observe the coefficients of the polynomial, then I can guarantee to you that BC over AD is always greater or equal to 9. I can guarantee this inequality to you. Now, this is actually kind of cool. Perhaps you could use it to maybe show that a cubic polynomial doesn't have 3 real roots such that they're all the same signs, i.e. all positive or negative. But we're not going to go into that just yet. We're going to focus on proving this, I don't know, cool inequality. Okay, so I've moved our inequality here. Let's prove it. Firstly, I'm going to call this polynomial p of x. So p of x is equal to the polynomial. Now, because p of x has the roots r1, r2, and r3, then we can write it in factored form. This would mean that p of x is equal to a times x minus r1 times x minus r2 times x minus r3. Like that. Now, you can expand all of this. I'm going to skip the details because, it's just expanding. And once you've expanded and collected like terms and factored, you'll see that this actually evaluates to. Now, what was the purpose of me expanding all of this just to get to this mess? Well, notice that we can compare the coefficients. Notice that over here, we've just deduced that this b over here is equal to this coefficient over here, right? Because they're both the coefficient of x squared, so they have to be equal to each other. And we know that this c over here, well, that's equal to this over here, right? It's the coefficient of x. So we're basically just comparing coefficients, and we're able to write each of these coefficients up here in terms of r1, r2, and r3. Okay, so let's write it out. Because this coefficient over here is equal to this b, with this negative, so be careful of that. But because this entire thing is equal to b, we may write r1 plus r2 plus r3 times negative a is equal to b. And we can actually divide both sides by negative a. If we do that, we would get that this is equal to negative b over a. And similarly, if you were to compare this with c and this with d, you would actually deduce that r1, r2 plus r1, r3 plus r2, r3 is equal to c over a. And finally, this compared with d, you would get that r1, r2, r3 is equal to negative d over a. Now, notice that, again, we're able to write these coefficients in terms of r1, r2, and r3. Of course, here we moved a onto the other side, but we've actually just derived, okay, I cannot write a bracket properly. We've actually just derived something called Vietta's formula. We've actually just derived Vietta's formula. Now, of course, if you were familiar with Vietta's formula, you could have just come up with this instantly. But this is the derivation for Vietta's formula. Okay, so I've numbered our equations. Now, this is where the magic begins. I'm going to divide equations. Specifically, I'm going to do equation 2 divided by equation 3. And this will give me, okay, now observe this. If we divide this entire side by r1, r2, r3, then notice that for this r1, r2 term, both of these will cancel out with this r1 and r2 down here, leaving with us with r3. So this would be 1 over r3. And over here, again, r1, r3 cancels out. R2 is remaining, so that would give us 1 over r2. And similarly, the last term just gives us 1 over r1. So that's 1 over r1. And on the other side, on the right-hand side, this would be c over a divided by negative d over a. Of course, the division by a's, they cancel out. So on this side, we just have negative c over d. Okay, so this is actually quite interesting. We've gotten another way to write the coefficients as the sum of the roots somehow. In this case, it's the reciprocals. But this isn't really that useful as of right now, even though it might look kind of cool. I'm going to focus on using this equation 1. Now I'm going to multiply both sides by equation 1, okay? And on this side, okay, on this left-hand side, I'm going to multiply this side by the r1 plus r2 plus r3. But on this side, I'm going to multiply by negative b over a. So on this side, let's multiply. This would give us r1 plus r2 plus r3, all right? And then times, the sum of the reciprocals, so that's plus, that would be 1 over r1 plus 1 over r2 plus 1 over r3. And on this side, I said I would multiply by this negative b over a, because they're equal to each other, right? So we can multiply by that. So this would be the negatives cancel out. That would just be bc over ad. Wait a minute. Do you notice something? Yes, this is the exact same expression we wanted to prove that was greater or equal to 9. How do we do that? Okay, so here's our expression. How do we show that this is greater or equal to 9? Well, we'll actually be using a very famous inequality. It's called the Cauchy-Schwarz inequality. I'll write it over here. This inequality is very famous. It's actually pretty useful. It's really cool as well. Over here, we have 3 terms in each of the brackets. So I'm just going to show what this says for 3 terms. Basically, if we have a sequence of real numbers, a1, a2, a3, and another sequence of real numbers, b1, b2, and b3, then the Cauchy-Schwarz inequality tells us that a1 squared plus a2 squared plus a3 squared times b1 squared plus b2 squared plus b3 squared. This over here, this entire thing is always greater or equal to a1 b1 plus a2 b2 plus a3 b3, all squared. And this is the Cauchy-Schwarz inequality. It might look a little bit complicated, but pay attention to how we form these terms over here. Notice that over here, a1 b1, it's just formed by a1 squared times b1 squared, and then we just take the square root of it. So we just get a1 b1. And that's the same story for a2 b2 and a3 b3. So really, we're just multiplying these 2 terms, right? And then just taking the square root each time to obtain each of these terms. And then we square the entire thing. So how do we use this to show that this is greater or equal to 9? Well, observe that. Observe that by Cauchy-Schwarz inequality, this is greater or equal to, right? Okay, I didn't time it right. This over here is greater or equal to r1 times 1 over r1, that's 1, and then take the square root, that's 1. And then r2 times 1 over r2, that's 1 again, take the square root. And again, r3 times 1 over r3, that's 1. And then square. Now, notice that this is just 3. And 3 squared is 9. So there we go. Here's a 9. And because this is equal to this, we know that BC over AD is always greater or equal to 9. And there we have it. We finally proved our original inequality. If you take the polynomial x cubed and then minus 4x squared plus 6x minus 12, I can guarantee to you, without even knowing what the roots are, I can guarantee to you that this polynomial does not have 3 roots such that they are all positive or negative. Why? Because take BC, that's negative 4 times 6, negative 24, and then divided by AD, 1 times negative 12. And you can see that this is 2, but 2 is obviously not greater or equal to 9, so this fails, right? So this actually does not have 3 real roots such that they are all positive or negative. You can check on a graphing calculator. The final remark I'll make is that this inequality extends well beyond cubics, and I'm going to show you how. If we take the general form of a polynomial, So that's an times x to the n plus an minus 1 times x to the n minus 1 plus all the way to a2x squared plus a1x and then plus a0. This is the general form of any polynomial. If we suppose that this polynomial has the real roots r1, r2, all the way to rn, so it has n roots, right? If we suppose that they are all real and they are all greater than 0 or less than 0, then we can similarly derive that an minus 1 times a1 divided by an times a0. This is always greater or equal to n squared. Now notice that this is really similar to this one. In fact, plug in n equals to 3 and you get this inequality. Now, I'm going to leave this as an exercise. It's really similar to this one. Just use Vieta's formula and then get something like this, and then use Cauchy-Schwarz. I'll leave the detail to you, but it's really cool. I encourage you to try it out. Anyways, thank you very much for watching this video. If you did find this interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.